Hello everyone, I'm Akira Fujimoto from Osaka University. The title of my talk is Stage 3 Matching for Detecting Code Move Across Files. At first, source code differencing is the differences in file content before and after the change. Well-known examples of source code differencing detection tools are diff in Unix and Gum3. In this research, we extended Gum3. Gum3 compares with before and after editing source code by using AST. AST stands for Abstract Syntax Tree. By using AST, Gum3 detects fine-grained source code differencing. In addition, Gum3 detects delete, insert, move, and update operations. This shows differencing detection of Gum3. In this example, method's name has been updated to get sum at line 1. A variable bar declared at line 2 has been deleted. A print statement has been inserted at line 7. And assign statement who equal a plus 1 moved into if statement. I'll explain Gum3 differencing detection. At first, Gum3 generates AST from each before and after change file. In the first step, Gum3 matches each tree. A matching tree is a process that associates AST nodes before and after the change. In this example, matched nodes are given same number. Gum3 calculates differencing by using the matching result. The nodes 0, 1, 2 are not changed because their nodes are same tree structure before and after the change. The node 3 only exists in AST before the change. Therefore, Gum3 outputs node 3 has been deleted. The node 4, the parent is changed node 1 to node 2. So Gum3 output as move. The node 5 only exists in AST after the change. Gum3 outputs node 5 has been deleted, inserted. However, Gum3 has an issue. That is, Gum3 cannot detect move across files. In this example, a developer moves print statement from main.java to sub.java. Applying Gum3 to each file, Gum3 outputs delete print statement in main.java and insert print statement in sub.java. However, more appropriate output is move of print statement. Due to this difference, developers may misunderstand that code change. There are many moves across file, like splitting function or code clone merging. Gum3 detects such a move across file as a deletion from a file and insertion to another file. In this research, our motivation is to detect differencing more appropriately. We hope developers to understand difference accurately. We expanded the detection targets by considering several files change at once, and so we detect moves across files. In the proposed technique, we construct a project-level AST from source files contained in the project. And then, the proposed technique calculates source code differencing by using project-level ASTs. Gum3 generates an AST from each source file, but our technique generates an AST from the whole project. I'll show you how we construct a project-level AST from several files. From file ABCD, we generate an AST from each file. Next, we create a root node that has each AST as its children. The project root node gets each file level AST together. By using this technique, we propose to construct two project-level ASTs from before and after the change, and calculate differencing. However, if we implement the technique simply, we can expect two problems easily. First problem is taking very long time to calculate differences, because a project-level AST becomes so huge. We exclude unchanged files which makes calculate time shorter. Second problem is increasing false detection because future project level AST is more the number of matching candidate nodes is increasing. We solve this problem by using staged matching. Before constructing a project-level AST, we compare contents of each file included in project. If the content of a file is the same between before and after the change, the file is not included in the project-level AST. At one change, only a part of files in the project are changed, so this strategy leads to reduce calculating time dramatically. Staged matching is to avoid false detections. In the first stage, matching is performed within the subtree of each file. This is the same matching as GAM tree. In the second stage, matching is performed for the entire of the project level AST. In the second stage, the matching targets are only the nodes that failed to be matched in the first stage. Staged matching aims to reduce the number of matching candidates in the second stage to realize non-appropriate matching across files. This is an example of staged matching. In this example, there are two candidates for matching focusing on line 2 in a.java. However, in the first stage limits matching candidates in the same file. Therefore, this int a equal 1 gets matched line 2 in a.java. Next, second stage enabled to matching across file. Method 2 in b.java before the change is matched with method 2 in a.java after the change. The output is like here. Method 2 was moved from b.java to a.java, and the statement int a equal 1 was added at line 7 in b.java. Next, I talk about the experiment that we conducted. The target software is 8OSS and contained in CVS Vintage and managed by Git. The first experiment is how much the number of moves across files proposed technique detects. This slide shows the results of the first experiment. The ratio of move across file to all moves is different from project to project, but our technique could detect move across files from all the projects. Now, I talk about experiment 2. In this experiment, we manually investigated across file code moves. We investigated what kind of code fragments are moved, difference on file contents before and after the change, and features of file information like file name. We found several features, so I'll show you some examples. This is a move method. Before change, class main has 4 methods, and method read and write moved into util.java. Move method like this. File names are likely to contain keywords like util or helper. Moved code fragments are not only for the method, but also are part of a method. This is an example that extracts a part of processing and moves to another file's method. The last example, class inheritance was changed. After the change, an abstract class A was added, and class C was modified to extend class A. Method 1 implemented in class C before the change had been implemented class A after the change. Therefore, the method 1 was moved from class C to A. We found several features like those examples. Conclusion. In this study, we propose a new technique of detecting code moves across file. Our technique is to construct a project-level AST from all source files in the project. We carried out experiments Our techniques could detect move across files. As a future work, we should apply our technique to other projects and visualize the detection results. That's all. Thank you.